depending on the vector psi. And what is this matrix? It's the projection onto the orthogonal of vector psi. Okay, so P of psi is the orthogonal projection on the orthogonal of the vector psi. Okay? So you project on fields in Fourier, you project on fields that are orthogonal to psi. But when you go back to the physical space, that means you project on divergent free field. Okay? And so then it's, of course, it's an L2 operator, it's an orthogonal projection in L2. So back to, the result follows by inverse Fourier transform. And so this projection P, this is called Leray projector. P is called the Leray projector. That's a projector in L2 over divergent free fields. Okay, any question? Okay. So then, last proposition is the so-called Helmholtz decomposition of N2 fields. When you have a field V in L2, V, you can decompose it as its projection onto vector field, onto divergent free vector fields, right? Plus some orthogonal part. And the Helmholtz decomposition tells you that this orthogonal part is a gradient for some Q with some Q in M2 log of RT. So, in particular, when you apply the Leray projector to a gradient field, it's 0. Because this is orthogonal to divergent free field. So when you apply P, this should be 0. And it tells you that anything that is orthogonal to divergent free vector fields is a gradient. So just a word about the proof of this Helmholtz decomposition. I will leave this more as an exercise. So, of course, for V smooth and decaying enough, how do you define P for this kind of very nice fields? We said that PV, that was V minus gradient delta minus 1 divergence of V. That's how we defined PV when the function was nice. But I have my gradient here. Okay? Let's call it Q. Okay? So if V is nice, V is PV plus some gradient field. Then when V is only in L2, can use the density argument. But there is a subtlety. Okay, so there is, and I will leave it to you as an exercise. Not so easy. Okay, so you see, the point in this Lorry projector here is to get rid of the pressure. You apply P to the equation. P of the pressure gradient is 0, and you are left only with something depending on U. But of course, P is a complicated operator, it's non-local in space, right? So you have difficulties associated to this. But at least you do not see P anymore in the equation, you have an evolution equation of U, which is convenient. So there is another way to get rid of the pressure, which is not applying the Lorry projector, which is applying the curl operator. So we can look at vorticity. So what is vorticity? So let me recall you what the curl of the vector field is. When you have a U from RD to RD, the curl of U so in fluid mechanics, okay, no, okay. So you mean curl U, you can denote it as curl U, you can denote it as lambda cross U. So what is it? What is it? In 3D, so as this notation indicates, it's the cross product of D1, D2, D3 with U1, U2, U3. So that's D2, U3 minus D3, U2, D3, U1 minus D1, U3, and last is D1, U2 minus D2, U1. Okay, that's for D equal 3. For D equal 2, what we call the curl will be a scalar. A scalar function which is D1 U2 minus D2 U1. Okay. If you want to see your planar flows are as flows in 3D with an invariant direction, the curl would be along this invariant direction, but you look at, it's given by only one scalar function, because you already know the axis, right? So you keep just that in mind. The vorticity of the curl will be a scalar. So in fluid mechanics, you have to think as a velocity field, and omega is, the curl of U is called vorticity field. Because you know locally, the curl is connected to the skew symmetry part of the Jacobian matrix of U. So it tells you how the particles under the action of U rotate. Okay, so it gives you vortices in fluid mechanics, so it's called vorticity. So in fluid mechanics, curl of U is called vorticity field, and most of the time people denote it by small omega. So what is the point with the curl? The curl when you apply it to a gradient, it gives you 0. So it's another way to get rid of the pressure in fluid mechanics equations. Okay? So this is another way to get rid of the pressure. So you apply curl to the momentum equation. Okay, so for Euler, when you do that, what do you get? Again, it depends on the dimension. So for d equals 3, what you get is dt omega plus u dot grad omega minus omega dot grad u equals 0. So remember that in 3D, omega is a 3D field. Omega 1, omega 2, omega 3. For d equal 2, so you have to make the calculation, right? It's not so obvious. It's an exercise. Find that applying the curl to the momentum equation, you have this. And when you do the same calculation for t equal 2, you can check that you get the following: dt omega plus u dot grad omega equals 0. So that's just the transport equation.